link your account to it, and you set up live. You do everything from StreamYard. I used it for 18 months or so, and it's literally foolproof. You don't have to worry about the audio. You don't have. You can if somebody's coming in to share screens with you, you have to give a permission, which means you can't be porn bombed or anything else, and it's all really simple.
Yeah, it's funny how, I mean, I think the thing is just like everything, you talk about it because it is simple, right? And you say those words, but the problem is that those words really do literally just like die this lonely death in my brain as they land, because what I really need to just see you pushing buttons and really know what those buttons are.
Yep.
I'll get you a link.
Yeah. Sounds like you could do it.
So how's everybody's weekend been?
So I had yesterday was the 40th anniversary of the day that I met my wife.
Aw.
Yeah. That was kind of fun.
That's cute.
Yeah.
We met at, can you guess? A Valentine's Day party.
Yeah.
Oh, yeah.
Excellent.
Nice.
Excellent. Thank you.
It looks good to me on YouTube.
Yeah. See, I'm not sure. I'm looking at it on my phone. I don't think I'm getting audio, but I can't quite tell because I'm trying to do too many things at once here. But it looks good.
It looks good to me on YouTube.
Yeah.
Yeah,
Okay.
I just heard me. Beautiful
Okay.
voice.
All right. Well, thanks everybody. And yeah, go ahead. All right. Thanks, Jesse. Appreciate it. So let's see. Let me get back into here. So what I'm gonna this is a reworking, as I mentioned, of actually I kind of put two presentations that I've given in my Bites of Physics series on Rayleigh's Criterion and on diffraction itself, which diffraction is really the physical phenomenon that informs Rayleigh's Criterion. So you'll see at one point I just kind of have some slides inserted in what was the original presentation, but I'll talk you through it. Hopefully it will make some kind of sense. So if we go to slide 1 here, this is kind of the overview. We're going to talk about optical resolution, and the idea of a point object is really important here. A point object is any object that is too small for us to be able to determine its angular size using a specified optical instrument. So stars, for instance, are point objects for our eyes. They're point objects for almost every optical instrument that we've ever built. There are a handful of stars that are big enough in angular size that we can actually resolve them. In other words, we can get pictures of them where the picture actually reflects their angular size. And in some sense, it's about stars that take more than one pixel. stars generally kind of show up as more than 1 pixel just because of resolution kinds of things and the CCDs, etc. But we can, in a very few cases, we can take a picture of a star where it actually does reflect the size of the star. There's several pixels, maybe 5 or 10 pixels across the star itself. And so when we take a picture of it, in some sense, we're really getting a picture that reflects its appearance. Whereas almost every star is just too far away, a combination of too far away and too small for an optical instrument to do anything but just see that some light is getting to us. And that's what a point object is. It's too small for us to be able to actually take a picture of it that reflects its actual angular size. And that depends, as I say, on the specific optical instrument used. So over there on the right, you see just a representation. Physical object might actually be like that, but we could see it as shown over on the right there as a much larger, blurrier thing, simply because the instrument we're using only has a resolution at kind of that size. That beta is the limit of resolution of the optical instrument. So it's really important to understand that just because it's too small to resolve doesn't mean that we can't see it. If light gets to us, if it's bright enough, we'll see it. If it's bright enough for our eyes to react to it and send signals to our brain, we'll see it, even if we can't resolve it. So we'll answer the following questions. What determines the angular size of an object? What determines when something is, quote, too small to resolve? Is resolution an inherent property of the light coming from the object, or is it a property of the optical instrument? And I'll just pause here for a moment and make clear. One thing that's really important to kind of understand is that an object emits light, and that light comes to us, and when we look at it, if we see it, it's because the light from it isn't being blocked. That light carries all possible information about the object, but then the instrument influences what we can make of that light. So telescopes are just much better at using the light that gets to us to take pictures of things. So I guess I'm kind of answering that question right now, but that's a really important question. And then is something that's too small to resolve invisible? Is it if it gets too small to resolve, does that make it invisible? When two small things or two small details of a single thing or the edges of two things get so close together that they can't be resolved as separate things, do they disappear? And this is really an important question for the idea of, does Rayleigh's criterion have something to do with sunset? Is it the thing that makes the sun disappear on the horizon? When things get so close together that they can't be resolved, does that mean that they disappear? I'm going to have a few remarks to say about that too. So I'm going to stop at just briefly at the end of each thing, because I don't want to just make the whole presentation and then take questions, although I can. But if there's any comments, go ahead. I'll stop for a few seconds. Okay, so this is an example I was just mentioning. R Doradus is a nearby star. It's 178 light years away. It only takes light 178 years to get to us from it. It's a red giant, has a diameter 300 times that of the sun, larger than the orbital diameter of Earth. So Earth is about 100 times the diameter of the sun away from the sun. R Doradus has a diameter of 300 times that of the sun. And you can take those two distances, the distance and the size, and work out the angular diameter. And the angular diameter is 14 1/millionths of a degree, which translates to 1/20th of an arc second. If you know anything about angles, you know that's a really, really small angle. our eyes can't begin to resolve things that are that small in angular size, but there are telescopes that can. So it is so far away that its tiny angular size does make it unresolvable for any telescope with an aperture less than about 100 inches. And there are telescopes with apertures that large. So there are telescopes that can resolve it. But you certainly would never resolve it with a pair of binoculars or an amateur telescope or anything like that. But it is visible. It's visible to the naked eye. It's a variable star. It varies between 4th magnitude and 6th magnitude. When it's 6th magnitude, you probably can't see it. But when it's 4th magnitude, if you've got a clear sky, you can see it. It's visible because it's bright enough that light gets to our eye and stimulates nerve impulses in our brain that respond to say, oh, there's a star there. I can see it. So that's what I'll say about R. doratus. Any comments there?
So is that like an optical picture of it?
That's a good question. I should have addressed that. I'm not. It is an optical picture of it, and I'm not entirely sure what all the this is how kind of blurry it looks.
Yeah.
But that's all that weird, structure is an artifact somehow of the telescope, maybe of supporting frames. It's kind of like what happens with the spikes and things like that. I'm guessing. I'm only guessing when I say that, but the size of that thing does reflect the size of our Doradus. And it's obviously more than a pixel, even though I think maybe the resolution is much more. The resolution is not at pixel size. But yeah, so I don't have a really good answer to your question. I found this picture of our Doradus, so I put it in here.
What
Well,
does
mhm.
angular size or angular diameter or whatever mean?
Good question. Do I know you, ma'am? So what determines
That's perfect timing.
what determines the angular size of an object? And then the answer is pretty simple. The angular size is just the width of the object divided by its distance. That's not strictly true for any object, but it's true as long as the angular size is small, and that is really to say, as long as the width is 1/10 of the distance, as long as that ratio is 1/10 or less, this is a really good approximation. I mean, it's good enough because angular size is always a little bit mysterious. Unless the object is a perfect sphere, angular size really doesn't mean anything because it'll have different sizes, in one direction than another. If it's an oblong object, its angular size will be bigger in one direction than it is in another direction. So you should really understand, as a physicist, we get used to saying things like, 532 is 500. 798 is 1,000, things like that, right? If you get within 5 or 10% of something, unless it's the kind of thing where that really matters, that's good enough. So when I say the angular size of an object is a degree, I mean it's somewhere between half a degree and 1.5 degrees or something like that. And small angles, this is always perfectly well. This whole thing is perfectly well defined for any kind of astronomical object. The angular sizes are so small that this is good enough. Technically, you should take an arctangent or an arcsine, but it turns out that an arctangent or an arcsine of an angle is equal to the angle if the angle is small. Now, the only caveat I'd say here is that the angular size that you get this way is given in a unit called radians. And a radian is 57 roughly degrees. So if I say that something has an angular size of 1/10, right, the width is 1/10 of the distance, so that the ratio there is 1/10. What I really mean is that the angular size is 1/10 of a radian, and 1/10 of a radian is about 6 degrees. So you have to be able to convert from radians to degrees, and calculators do that kind of thing, and most of you probably know of that. And so I've given a few examples there. The average angular size of the sun is just its diameter divided by how far away it is, which is the average radius of the Earth's orbit. So I take the diameter of the sun, 867,000 miles, divide by the 93 million mile distance, and I get 0.0093 radians, which when I multiply by the 57 degrees per radian gives me 0.53 degrees, which is the same as 32 arc minutes. There's 60 arc minutes in a degree. So half a degree is about 30 arc minutes. It's a little more than a half a degree, so it's 32 arc minutes. And interestingly, of course, as we all know, the average angular size of the moon is pretty much the same because of this coincidence that the ratio of the diameter of the moon to its distance from us, the radius of its orbit, is also about 0.009 radians. On average, it's about 0.52 degrees, 31 arc minutes, but you can see that they're basically the same. And because the distance to both the sun and the moon change during the year, sometimes the moon's a little bigger than the sun, and sometimes it's a little smaller than the sun, but it's correct, especially for a physicist, simply to say the sun and the moon are both, if the sun or the moon is in the sky, it is a thing with an angular size of half a degree. It's not exactly right, but it's never a quarter of a degree, never 3/4 of a degree. Those things never have sizes as small as a quarter of a degree, never have sizes as large as 3/4 of a degree. They're always a half a degree. And then because it's fun sometimes to, we have a weird idea about the size of those things, and you can see that if you see the full moon sometime, hold your little finger out, you'll see that you can easily block the moon with your little finger held at arm's distance, because it has an angular size about twice that of the moon. It's easy to block out the sun or the moon with your little finger held at arm's distance. And once again, I'll stop for a second. So did that answer your question, Coco, about angular size?
Kind of.
Yeah, well,
go ahead. Maybe just a little more bad at math and stuff than most people. So I might have to try to go over this myself.
Well, you notice that the drawing there, I show a really weird object that doesn't have a really perfectly well-defined distance, right? Because the near part of it is nearer and the far part of it is farther. But it also, it's, and especially if I was looking at it from the place where the red lines converge, if I was looking at it from there, it's relatively narrow, looked at from that direction, but it's also relatively long along the distance. So the distance isn't very well defined. The angular size is really determined by how wide it looks. the maximum distance. I didn't even draw those red lines quite right. But at any rate, fundamentally, this is why you have to take angular size with a grain of salt. To look at the red lines, just take the distance from where they converge over there at the left, all the way to, kind of where the object is, where is it? I don't know. It's kind of along that line somewhere. And then take that bold red line perpendicular to the two red rays. That would be the actual width. Divide the length of that bold red line by the distance of that bold red line from the place where we're looking, which is over there at the far left, and that would be the angular size. Yeah. And you can just read it off. It's a few degrees there. Go ahead.
A way I like to think about it, Coco, is if you imagine when you look around yourself, when you swivel your head, you kind of have a sphere of vision around you. And if you broke that sphere into 360 little divisions, each of those divisions have the size of 1 degree of angular size. So if you took 700, because the moon is half a degree, If you took 720 copies of the moon and put them all next to each other, they would complete the circle around you.
That's right. And kind of in the same way, I often like to talk about refraction at the horizon by pointing out that if there were no atmospheric refraction, you could put 360 moons from horizon to horizon, 180 degrees from horizon overhead to the other horizon. You could place 360 moons right next to each other, encompassing that 180 degrees. But because of atmospheric refraction, which allows you to see a little bit around the corners of the Earth, you can stick more than 360 moons in that distance. And that means that some of them have to get compressed vertically. And that's what happens at the horizon. The moon and the sun get compressed vertically a little bit because of refraction. And that may have been more than we should talk about here. But anyway, that's a good thing too. But I like that. I like that same kind of analogy. Okay. So yeah, go ahead.
No, go ahead.
Okay. So excuse me, what determines when something is too small to resolve? And the answer is, in a word, diffraction, due to the finite aperture size of the instrument being used, also due to the wavelength. And I had in my original presentation here to recall from a previous bite of physics on diffraction. So what I'm going to do now is to just insert some slides from that diffraction thing. And so this is a little bit of an aside. The next 5 or 6 slides will be a little bit of an aside on that whole question of where this Rayleigh's criterion comes from, why diffraction is the thing that determines resolution. And so we have to back up a little bit and talk about a thing called the Huygens-Fresnel principle, which is this idea that if you have a wave, this is true for water waves, light waves, sound waves, any kind of a wave. We talk about wave fronts, like if you see waves coming to the beach, you see, the high amplitude wave coming and crashing on the beach. Waves propagate perpendicular to their wave fronts, and I'm showing that over at the right there. The vertical red lines are wave fronts. They're propagating toward the right. But what I'm showing is that on that first wave front on the left, the long one, I just take kind of every point on that wave front and then draw little circular lines around it, centered on it, because every point on that wave front becomes a source, a little point source of light for according to the Huygens-Fresnel principle, for propagating the wave forward. So if I look at the intersections of all of those little circles drawn on points on the wave front, they end up interfering constructively, and I'll say more about constructive and destructive interference here in a moment, along that new red line. So that new red line becomes becomes the new wave front. If you look at all of those little semicircles, you'll notice that on the new wave front, it's all the little that new wave front is all positive wave fronts adding together, whereas in between the two, there are places where you have wave fronts interfering, being at the same place as the place between other wave fronts. Maybe I should say this another way. Imagine you were on a rowboat in the ocean and waves are coming by you. You're bobbing up and down. But if there's another set of waves coming from another direction, you're going to bob up and down kind of due to the sum of those two waves. And sometimes both of those waves will be lifting you up and you'll go doubly high. Sometimes both of the waves will be going down and you'll be doubly down. So the high amplitude oscillations up and down because of that. But you can also be at a place where one wave wants you to go up while the other wave wants you to go down. And the net result of that is that you don't go anywhere at all. It's like there's no wave there at all. And that's kind of what's going on in the space between these two red lines. Some of the waves want you to go up, but some of the waves want you to go down. They're interfering, we say, destructively, and the net result is that there's not much going on there, whereas up there at the front, where you have nothing but waves that want to take you up, that you get essentially the new wavefront. There's much more complicated stuff going on here than I'm even able to kind of enunciate. But this is kind of an important idea for what comes next. I'll stop here for a second, but maybe the next slide may help. Okay, so for instance, if I have light coming from something that's very, very far away, the wavefronts are all, I'm showing once again red wavefronts that are traveling to the right, separated by what we call the wavelength, right? The wavelength is the distance from one peak in the wave to the next peak in the wave. So you can kind of see what the wavelength is there. Think about waves coming into a beach if you want. And this could really be water waves as far as that's concerned. These water waves are traveling, those wavefronts extend infinitely far if you want, to the top and the bottom. Doesn't really matter. Those wavefronts can be as long vertically as you like. That doesn't matter because they're approaching a barricade. And I'm showing a barricade, the dark black, extending upward, and the dark black extending downward completely blocks any part of the wave, above this diagram, below this diagram. The only part of the wave that gets through is the part that you see there with the numbers next to it in the what we call the slit or the aperture. This is really an aperture, an opening through which the waves are traveling. So it's only for to try to figure out what happens on the other side of this aperture, this slit. Well, all I need to do is now take the fact that there's a limited number of points on that wavefront that are acting as new sources and ask what the net result of that is at some point. So for instance, if I'm observing this wave at that observation point, by the way, are you seeing my cursor? Does that show up?
Yeah, it is.
Okay, good. So if I want to know what's happening at that observation point, I have to add the contribution at that point from the place here that I've labeled 0, plus the contribution from this other place that I've labeled 0.22. I'll explain that in a minute. Plus the contribution from the place that I'm calling 0.51, plus all the others, right? All the others in here as well. It's not just these. I have to add up all of these contributions. And the problem is, for instance, if you just look at the 0.51, that means that the distance from this place, the 0.51 to the observation point, is 0.51 wavelengths longer. This distance between the green shaded area and that is about a half a wavelength longer than the distance from the 0 point up to the observation point. And that means that when the contribution from this place gets there, it's going to be 1/2 of a wavelength, so-called out of phase, with the contribution from this point. And what that means is that this contribution and this contribution will basically cancel completely. This one's going to be going down when this one's going up, and this one's going to be going up when this one's going down, etc. So these two cancel each other. And if you think about that for a moment, you'll notice that means that the little point slightly below the 0, is going to perfectly cancel with a little point slightly below the 0.51, and so on. In other words, most of the contributions along here have a partner that they team up with that cancels completely. In fact, when I get to the 1.0, I didn't label it, but there's a place here I could label 1.0, a place that is one wavelength further, this distance from the green to it. That distance is one extra wavelength. If I, within the bulk of the slit, most of the contributions up here at the top part have a partner down here in the bottom part that they completely cancel with. So the only contribution at the observation point comes from just the very bottom part here, where there's some contributions that don't have a canceling partner. Now, I said a lot of stuff there, and I'm not even sure. It's not going to be completely important that you fully understand that. But if you have questions, if there's some way I can kind of help you appreciate that, let me try to do that.
No, I think maybe just continue and see how it all fits together.
Yeah. So, but this is this idea of the various parts of the wavefront in the aperture interfering with each other at an observation point is kind of the central idea. So let me show you a little bit more here. For instance, if I'm adding a bunch of sine waves, a bunch of waves, and they're all nearly in phase. Notice what I mean by nearly in phase is, to a pretty good extent, when one peaks, they all peak. It's not exactly at the same place, but it's kind of at the same place. And when one troughs out, they all kind of trough out. So if I add up all of those sine waves, what I'll end up getting is another sine wave, a sine wave with slightly less amplitude than they would have if they were perfectly in phase, but still a pretty good sine wave, because when one is up, they're all kind of up, and vice versa. Okay, that's really the point. Here in the middle range, I've got a bunch of sine waves where there's almost all phases represented. There's just a small number of phases. You can kind of see in this region, there's some sine waves that I haven't drawn, which is to say that in this region, they're all kind of generally upward, but you'll notice that they don't peak at anywhere near the same time. They all kind of peak, and then kind of when they're done peaking, they all start kind of troughing, but over a large range. There's a lot of cancellation in here because they're not in phase like they were, much more so in the top. And that means that when I add all these up, I'm going to get a lot of cancellation. I'm still going to get a sine wave. It's going to be generally up when they're all generally up. It's going to be generally down when they're all generally down, but it's going to be a smaller amplitude sine wave because there's so much more cancellation going on. Whereas at the bottom now, I've shown just equal contributions from all phases. There's a sine wave happening at every conceivable phase along here. One peaks, then the next peaks, then there's another peaks, another that peaks. There's always a sine wave peaking. There's always a sine wave troughing. And when I add these up, I get nothing. I get a flat line because there's always something that's doing just the opposite of whatever any specific sine wave you point to is doing. So when you get that kind of a situation, you end up getting no wave at all. And if this is light, it really means that I can add up a bunch of different sources of light and end up getting no light, because at a point there would be no illumination because the light is canceling out other light. Same thing happens with water waves and sound waves. You can do these kinds of things with all wave phenomena, but it seems a little odd with light somehow. You could actually shine a bunch of light at a place and find that it's dark, because all of those light, if you have what's called coherent laser type light, you can actually do this and get the light to cancel itself out and be dark. So hopefully this slide kind of helps you at least understand that idea of phase cancellation, phase constructive interference up here at the top, destructive interference down here at the bottom. And I will move on in a moment here. Okay, so this slide then shows kind of in a little more detail the kind of thing we're talking about. If I have this plane wave coming into this aperture, and beyond the aperture, now let's really think about light. Wavelengths of light are really small. So this aperture that I'm talking about being what 5, 6 wavelengths or something across, about 5 times as far as the distance from one wavefront to the other. This is a really small aperture. And as a result, it's almost like it's just a little pinprick in this screen in the barricade that light gets through. And now I want to look at the result at a screen on an observation point that's fairly far away. So I've actually drawn this jagged line to represent the fact that I'm looking at a highly magnified version of the slit here. But now I want to look at an observation point that's maybe, a meter away or something, maybe 3 or 4 feet away from a hole that's really tiny in this barricade. So all of this light that's headed off looks like it's going parallel. The only reason it looks like it's going parallel is because it's all going to this point that's really far away relative to the size of this slit. And as a result of that, I can make a nice kind of approximation, just draw a line perpendicular to these rays of light that are going to the observation point, and talk about the interference in terms of just this extra path length. From the green line on, they all go the same distance, and so there'd be the same number of wavelengths that would occur. If there's any phase difference at the observation point, it's because of the extra distance that each of these numbered sources have to go through. 1, 2, 3, 4, 5, up to 11, have to go through successively slightly larger distances. And what I'm suggesting is this light brown region is the region that starts with no extra path length and ends at 1 wavelength of extra path length. So in this region, for every point that contributes something at the observation point, there's another point that's exactly out of phase. So every single point in this region cancels with some other point in that same region. So I can completely X out this region and just say it contributes nothing at the observation point. The same thing is true for the green, because it starts at 1 wavelength of extra distance and ends at 2 wavelengths of extra distance. So this green portion contributes nothing. Every point here has a canceling point. Same thing's true for this purple thing. It goes from 2 wavelengths at 7 to 3 wavelengths at 10. All of those cancel completely. So there's no contribution from any of the kind of brown, gray, whatever, green and purple, pink parts. The only part that contributes anything that doesn't get canceled is this little blue section down here. So there's going to be very little light at this point compared to the central point, because notice at the central point, all of these rays would be going exactly horizontally, or very close to exactly horizontally. So they'd all go the same distance to the central point. They'd all add up. I'd have 11 times as much light getting to the central point as I do getting to this point, just because there's no cancellation at all. So let's see, what else did I say here? Okay, so I actually put some numbers on here for you. So this is probably the hardest part. We're going to start seeing where this leads to in the next slide. But any comments, questions on this one? Takeaway is that when I move away from the central point where I'm going to get a really bright light, I'm going to get less and less light over here. But it's a little more complicated than that. You end up getting a pattern that looks like this. If I just draw the intensity of the light on the screen, you can work this out mathematically. You don't have to go through this. Forget about anything I've written over here. The important point is that this graph shows you how bright the light is on the screen. And it turns out that you get very bright light right at the center. It falls off to literally 0 at this place, the place that I write as the arc sine of lambda over d, but turns out when lambda over d, the wavelength of the light divided by the diameter of the aperture, the size of the aperture, that wavelength divided by aperture, we're going to see over and over again. When I get to a place where the arc whose sine is lambda over d, at that place you get perfect cancellation. And if lambda is much smaller, if the wavelength is much smaller than the aperture size, arc sine of lambda over d is lambda over d. So you can pretty much forget about the arc sines. Just write lambda over d, wavelength over d here. But then what happens is after that point, you start getting some light gets through again, because you're now in a region where a large part of the slit is canceling itself out, but there's some now that is uncanceled. So you get a slight secondary maximum, and then you get another place where you get perfect cancellation, and then a slightly smaller little peak, and so on. But you'll notice the really important thing is that what you end up getting is a central spot, a very bright central spot that extends from lambda over d, wavelength over aperture size, to negative wavelength over aperture size, if you want, down here. And in some sense, you can think of that spot as being the image of the thing that was creating the light in the first place. So let me just go, oh, sorry, I guess let me go on to this slide first. So this is kind of giving you an example of that. There's a lens here. Unfortunately, I'd have to explain its use. Forget about the lens if you want. The important point is you have a very distant point object, let's say, very distant, much more distant than I'm showing here, producing this light that comes into this aperture. The light is coming into these wave fronts, these parallel planes of wave fronts into this aperture, and then producing this big central spot on the screen. In some sense, that spot is the image created by this optical instrument of that object. So that distant point object, but the aperture itself is responsible for making it this big kind of blurry, if you want, blob on the screen. This is the image of that point object. And you'll notice its size doesn't have anything to do with the size of the object. It has only to do with the wavelength of the light and the aperture size. Here I'm using A rather than D, sorry, for the aperture size. But the only thing that determines the size of that image is the wavelength and the aperture. The size of the object has nothing to do with it. I'll just show you that example here. If I shine a laser through a little slit, you get an image that looks like this, a very bright spot that's twice the size, notice, of this secondary maximum, this tertiary maximum, etc. You get a bunch of dimmer and dimmer secondary maxima off to the side. But this is that central spot, very bright, extending from the middle of the screen off in each direction to an angle of wavelength divided by aperture. And in the bottom here, you'll see I've got a very small slit width creating a very large central spot. As I make the slit width larger and larger, the central spot gets smaller and smaller. That's the key thing. I'll stop here when I'm done here, but I just want to say this really clearly. Notice that given this wavelength, this is red light, 600 nanometer light or something like that. Given this light, a very small aperture leads to a very large image, if you want, of the object that's creating the light. And as I make the aperture larger and larger, the size of the image gets smaller and smaller. I start getting more resolution, if you want. The spot here is much smaller than the spot was when I had the small aperture. So making the aperture larger and larger helps me get more resolution. That's really the lesson of this. Now I will stop for a moment.
So I have a quick question here.
Yeah.
So my telescope, it has a secondary mirror in front of the aperture. Uh, is I don't know if you can tell me if you know this. Like, would the angular resolution of my telescope still be um the same without it, or would that central obstruction cause there to be less angular resolution?
So you actually have, let me understand, is this a Dobsonian? What is this?
It's a Schmidt-Cassegrain.
Okay, I guess I said that like I would really know what that even meant in terms of construction. I'm not sure. I understand why you would. Yeah, I would. My answer without seeing more of the details would be that the resolution is ultimately determined by whatever it is that limits the aperture. So if the aperture is determined by something other than the opening at the front of the telescope, then I think you're sacrificing resolution. But maybe I'd have to look at the design more to understand that.
I mean, it's close enough to a Newtonian. It's just where a piece of glass is holding it instead of the four metal veins.
Yeah, so it's probably just, it's not enough of a difference for it to make a difference. I wouldn't think they would put anything in the light path once it's entered the telescope that would restrict the aperture further. That would seem to be counterproductive. Yeah, and so now we really need to see. I've been talking here, of course, about just kind of a one-dimensional slit or something, an aperture in a one-dimensional way. We need to talk about circular apertures now, but all of the concepts carry over. The math gets more complicated if you want to follow it because it involves Bessel functions. But we're not going to talk about that. And I'm just going to tell you that there's a number that comes in, a 1.22 that comes in as a result. That's really all that matters.
Yeah. I was just wondering if it's more like the area of the aperture.
Yeah,
Possibly.
well, so in some sense it is, right? If you make the area of the aperture larger, in general, you're going to get more resolution. But you want that resolution. The problem is that if the aperture, for instance, were elliptical, then you'd have nice resolution in one direction and less resolution in the other. There's all sorts of reasons not to make a telescope have an elliptical aperture. Yeah. Okay, so we're now really at Rayleigh's criterion. I've been talking about the ratio of the wavelength to the aperture size, the diameter, just the aperture size, let's say. And it turns out that Rayleigh's criterion, because it's for a circular aperture, because circular apertures are what optical instruments have for kind of obvious reasons. Our pupils are circular apertures. Telescopes have circular apertures. Binoculars have circular apertures. Oh, what did I do? I lost it here. There we go. So we need to know what the equivalent thing is for a circular aperture. And what I'm showing here are images of 2-point objects. Imagine a point object, 2-point objects that are separated by some distance. Think about, I should have shown one first. I'm sorry that I didn't. If I had 1-point object, let's just concentrate on this bright spot on the left. And the rings around it. Try to forget that there's the bright spot on the right and the rings around it. Just look at this bright spot on the left and the rings around it. that is what the pattern of a circular aperture looks like. And it's very much like what I talked about before, a very bright central thing with a much smaller secondary maximum, and then a tertiary maximum, and so on, with places where the light exactly cancels. And this is exactly the same idea. It's just that the way that it's not as simple as just saying, okay, I've got this point here and then this point below it, et cetera, like I did with the slits. Now we've got really an area that we have to deal with. And this is what mathematically leads to the description of this pattern in terms of what are called Bessel functions. And the only difference for our purposes is that the distance from the center out to this first maximum is now not wavelength divided by aperture size. It's now 1.22 times the wavelength divided by the aperture size. The distance from the center of the spot out to the first zero is 1.22 times the wavelength over the aperture size. And that 1.22 comes from a zero of the Bessel order of the first kind, which is, once again, none of which matters. For my purposes, even the 1.22 doesn't matter. We want to get an idea about resolution. So even for circular apertures, if you just want to ignore the 1.22 and use wavelength over aperture size, that's really perfectly adequate, especially for reasons like that I'll mention here in a moment. Rayleigh's criterion says that when the distance between the central spots of two images of two point objects, so now we have 2 point objects being imaged here, when the distance from the center of one to the center of the other is equal to the distance from the center to the first maximum, when the separation is equal to the radius, separation of these two sources is equal to the radius of the first zero here around the maximum, then the objects are just resolved. So in this top picture, these two objects are resolved because the distance from the center of one image to the other is twice the distance from the center to the first null, the first zero here, right? The blue and the red lines are both that radius. So these two objects are separated by twice the distance specified in Rayleigh's criterion, whereas these two objects in the middle panel are separated by exactly that distance. This is what Rayleigh's criterion would say. These two objects are just resolved. If they were any closer together, they wouldn't be resolved. And if they're any further apart, they are resolved. So down here in the bottom, they're closer. The two centers are closer than that. And therefore, by Rayleigh's criterion, the 2 point objects are not resolved. And I think you would agree that you don't see two images there. Although you would probably also say, there's something weird about that image. It's kind of wider than it is tall. If that is 1 point object, well, I can look at that and say for sure that it's really not 1 point object. So in some sense, I know there's two objects at least there's an extended object creating this image, but they're not resolved. And all I'm really trying to say by this is Rayleigh's criterion is kind of arbitrary. Is this as close as they can be before you know for sure that there's two objects? I would say no, they can be closer than that. You still know that there's two objects. But this is the point at which Rayleigh's criterion says they are now no longer resolved. And you can kind of see why. When they get further apart, you can really see that there's two things. Whereas here, it's kind of two things glommed together. And here, it looks a little more like one thing. Okay, so I'll stop there for a moment. And we're getting pretty close to the end, frankly. Okay. Yeah, go ahead.
I am probably going to be looking over this again on my own time, and then maybe dragging you over here one of our BC nights and making you answer questions.
Yeah. It's always happy to do that.
Yay!
But I think forget about the complicated parts really at some level. Just the important thing is to remember that, look, for instance, what would this middle thing look like if I had an aperture that was much bigger? Well, let's think about that for a second. If I looked at those same 2 point objects that are shown in this middle diagram here in this image, using an optical device that had a much larger aperture, what that means is that the distance, the radius of this first dark circle, right? The radius of this first dark circle is wavelength divided by aperture. That is the wavelength divided by the aperture. The length of this red line, the length of this cyan line, those both have a length equal to wavelength divided by diameter. So if I make the aperture diameter bigger, both of these lines get smaller, and that means that each of the images is now a much more compact, bright, small image. And so if you think about what this middle thing would look like, now it would look more like this, more like the top one, just at a smaller scale. Both of those spots would be smaller. They would be much more clearly distinct. I would see them much more clearly as 2 objects. And that's what the diameter buys you. When you make the aperture diameter larger, those spots get smaller, so you can see things more sharply. Things get better resolution. They're sharper because those spots are now smaller. That's just a direct result of the aperture, the diameter here in the denominator getting larger, making its ratio smaller. And I can do that as well by using smaller wavelengths. If I use smaller wavelengths, I'll get better resolution as well. But in the visible range, we're limited to pretty much wavelengths that don't vary very much. The smallest wavelength we can see is about 400 nanometers, and the largest is about 700. So you only get about a factor of 2 in the visible range. You don't get much. You can get a lot more by going from the diameter of a human eye 2, 4, 6 millimeters up to a telescope with a diameter of 10 meters. You have a telescope with an aperture that's 1,000 or 10,000 times larger than the human eye. You get much better resolution. These spots get much, much smaller. Okay. So let's talk about the diffraction limit, this Rayleigh criterion thing of the human eye. And as I say, although there are other factors that determine whether or not we can make out an object visually, the human eye has a pupil that ranges from 2 to 8 millimeters, typically about 4 millimeters in diameter, and it processes light of wavelength 400 to 700 nanometers. That's not a large range. So if I take that range of diameters and wavelengths, I get that the Rayleigh's criterion gives us an angular resolution as small as maybe 0.2 arc minutes up to as large as 1.5 arc minutes. When we're in the dark, our pupils enlarge, right? They dilate. So we get better resolution. Unfortunately, there's not as much light. In bright light, our pupils narrow down and we get less resolution. But this 0.2 to 1.5 arc minutes to a physicist, I would just say it's about an arc minute, right? The resolution of the human eye typically is about an arc minute, 1/60th of a degree. And to really appreciate what that means, because it's hard to appreciate angles like that, remember that the sun and the moon are both always very nearly half a degree in diameter, 30 arc minutes. So the resolution of the human eye is much better than the size of the sun. When we look at the moon, we can see details on the moon because our resolution is, 30 times better than the size of the moon. If you think in terms of pixels, 30 pixels across, 30 pixels up, you've got something on the order of 1,000 pixels of resolution. Just looking at the moon, it's like you were making 1,000 pixel image of the moon. That means they're really well resolved. You look at the moon, it's really clear that you can see that it has maybe not craters, but you can see the mare, the dark and light areas, the man in the moon thing, and all that kind of stuff. Very well resolved. Okay, so this whole question of the sunset, then, what I've shown here is kind of an enlarged version of what the sun and the horizon look like. The sun is 32 arc minutes across. The resolution, when we look at the horizon and the sun with our eyes, what we see is something like this. There's a blurriness at the level of 1 arc minute. We can't resolve things less than 1 arc minute. So the edge of the sun is blurry at the level of 1 arc minute, as is the horizon. We get used to thinking when we look out at stuff, if we have good vision, we say, that's a really sharp edge. Well, a really sharp edge is blurry, like this, at the level of 1 arc minute. That's some indication. Just look at a line near you. Look at something in the room that looks sharp. That sharp thing is blurry at the level of 1 arc minute. And you, rather than look at that and say, no, it isn't, you should just understand that what I'm telling you is that 1 arc minute is a really tiny angle. It is blurry at the level of 1 arc minute, but because you've never seen anything sharper than that, you say that's sharp. So the horizon is blurry at the level of 1 arc minute, and it looks perfectly sharp to you. But notice that there's no question about the sun. The sun is way bigger than that blurriness. So when you see it halfway down to the horizon, it's not halfway down to the horizon because you can't resolve things. Right? There's a half of the sun that is 30, is not 30, is 10 or 15 arc minutes below the horizon at that point. It's not merging with the horizon because of Rayleigh's criterion. At least it's not that. And I've got a link there to, I'll put a link to this presentation so that you can click on those links and not have to copy them down and write them in.
I'm pretty sure you did, but please feel free to post anything at any time that you want to.
Thank you. I think I have, let's see, do I have, wait a minute, I'm going the wrong way. Let me go this way again. Oh, no, I'm not. Oh, I think I am done. Yeah, I think that was it. Oh, no, I did. That's right. I have 2 things more. That's right. So do things disappear when they're not resolved? And so I've got here, this is a thing that I think we've all seen if we drive along a desert road or, a road that has ups and downs. We're driving at night. We can see the headlights of an oncoming car, even if it's on the other side of a local peak that we're about to go over, just because light gets kind of scattered into our eye from the atmosphere above. The light is shining on the atmosphere above that peak. So you can see kind of the blurriness here, 1 and 2. You can see, there's a car coming. And if you got your brights on, I probably better put my brights down because I'm going to see a car. I was going to see my headlights here pretty soon. As the car emerges, the moment that the headlights are now no longer obstructed by the road, you're going to see them. And I'm talking here about a case. Let's see, what did I say? Oops. I guess I didn't put numbers here, but I think this would typically be if this would be a situation where you've got typical car headlights separated by 6 feet or something, 5 or 6 feet, on a car that's maybe a few miles away. if you work out what that means, a car 5 or 6 feet at a distance of several miles turns out to be something getting pretty close to Rayleigh's criterion. So in number 3 here, I'm showing you these 2 headlights that are not very well resolved. They're kind of right at Rayleigh's criterion. There's no question you see them. The moment that car pops up such that the headlights are not being blocked by the horizon, which is a different thing, has nothing to do with Rayleigh's criterion. The moment that light has a path to get to your eye, you see them very brightly because they're there. They're bright enough to see, especially at night. And there's no question that you see them. And of course, as they come toward you and get a little higher, you might see them a little more clearly. But the big difference here has nothing really to do with the fact that you can't resolve the headlights. The big difference comes from 2 to 3 when the headlights go from being blocked by the earth to not being blocked by the earth. The moment they're not blocked, you see them brightly. And then the resolution is just another whole thing that has nothing to do with whether you see them or not. So how do things disappear from the bottom up? And as I say, things disappear from the bottom up because they go beyond and then below a physical object that blocks their light. The only way not to see something is for it to be to not to be able to see something, is for the light from it to be physically blocked. Now you may not, as long as it's bright enough to see and the light isn't blocked, you're going to see it. It's that simple. And I think the thing that the final closing thing I'll say is just that the light coming from those headlights carries all the information about them. If you had an optical instrument with enough resolution, you could see every detail in those headlights. If the light were on, if it were daylight and you were looking at that car and you had enough optical gathering power, you could see the relief on the glass of the headlights, etc. All of the information that's available is in the photons that are coming to you. You can't change what it is that you're able to see by putting something in front of your eyes. This idea that somehow you can put a telescope in front of your eyes and bring something back from over the horizon suggests that the light from that object wasn't even there until you put the binoculars in front of your eye. And that's silly. The light doesn't know whether you have binoculars in front of your eye or not. The only reason you can't see something that you can with binoculars is just because it's too small to resolve or to make out, or maybe its color is too close to the color of the stuff that's right next to it, next to the ocean or something. But put a light on an object, have it be night, have it be bright enough to stimulate your eyes, and you'll see it unless it's being blocked. Okay, so I'm preaching to the choir, I know, when I say all that stuff. But that's it. I'm done. So I'm happy to take more questions or whatever you like.
I just wanted to say the slide with the single slit, that really made it click for me.
With the lasers, you mean?
Mm-hmm.
Yeah. Oh, good. Yeah. Yeah, I think that it's that inverse relationship. It's the fact that when you make the aperture bigger and bigger, the spot gets smaller and smaller. That's kind of counterintuitive.
Yeah, but no, that was a great slide to have.
Well, then I'll go back to it. Let's see. There.
Yeah, I saw that. I was like, oh, okay. Yeah.
Yeah, it's really interesting because you can see right in this top left one, the actual physical mechanism. There's a slit here with a little thumb screw that lets you adjust the size of this little slit. You shine a laser light on it. The slit is, a fraction of a millimeter wide. And then you see the light extending out and going on to and just imagine making that slit larger and larger. All of these little rays get closer and closer and closer. It becomes a tighter and tighter pattern. In fact, you can really imagine if I make that slit really large, what does it look like on the other side? It just looks like the laser beam. Right? Laser beam's just going through the slit, right? So that it's the counterintuitive thing is that the smaller the slit gets, the more it spreads out this pattern by diffraction. The smaller it gets, the wider everything over here gets.
Great presentation all around.
Thank you.
Yes, thank you so very much.
Let me give you a. Oh, I don't have soundboard permissions. I was going to do a clapping sound.
I hear it.
You don't have soundboard permission? I thought we.
I don't have a lot of permissions. You just don't like me, I think.
Well, that actually could be true.
Oh, look at that. See, now that's another thing I don't even know how to do. Hey, Shoebill. So I see you popped in. So, Jesse, I don't know if you're there. We can stop the live stream if you want, if you are there.
Oh, no.
Nope.
He had to step out, so that is just his live stream running.
Mm-hmm.
He
Okay.
did say to remember that any after discussion we have
Mm-hmm. Is going
live
out there.
stream yes.
Yeah,
yes,
watch your guys'
so
mouths.
we
I
can
clicked in.
hop over to the non-live VC if you wanted. I'm sorry, Shoebill, go ahead.
I clicked in kind of late, only for about the past half hour. It seems like it was very, very detailed and technical. One thing you made a comment a second ago about all the information of, like, say, the headlight. If you had proper optics, you could even see the prismatic or even the logo on the glass. But what about diffraction, to where,
Yeah,
no matter what you do, the turbulence of the air column has just blurred it permanently?
okay, right. You said diffraction, but then, which is a slightly different thing from turbulence of the air column, right? The turbulence is another issue that I didn't even talk about. And of course, that will cause, that's always going to be the thing that ultimately limits your ability. And that's why Mount Wilson was built where it was, even though it's near Los Angeles and all that, happens to be stable air for kind of meteor, topographic reasons. But yeah, forgetting about turbulence, though, what I meant to say there was just that the light coming from the headlights carries information at whatever detail you wanna talk about. It's now your job to extract that information by, if you need to see the actual structure of the glass itself, well, you'll need to have a really big telescope to be able to, have an aperture that's large enough to give you that resolution. But the thing that's really key is understanding that lack of resolution has nothing to do with the light coming from the object, other than its wavelength. The resolution is just a matter of the optical instrument, so that as you make the diameter of the aperture bigger and bigger and bigger, you get more and more and more resolution. You get resolution right down to the photon level, if you want.
Because, like, in my application, of course, you all know I'm, particularly with survey instruments, and a favorite target is the strobe light on a radio tower. Now, the strobe light, physically is less than an arc second subtended angle. But when looking at it from, say, 20 miles away, it's like a cotton ball. It's much bigger than the single arc second. Is that
Mhm.
diffraction?
So probably, well, I don't know. What is, so that's a good question. What is the aperture of a surveying device, surveying telescope?
Well, the forward lens is barely 1.5 inches, maybe 1.25 inches.
So let's see, what's that? 40 millimeters or something, 30, 40 millimeters.
Okay. And the
So,
telescope length is, maybe 4 or 5 inches, and the magnification is about it's either like 24 or 40.
yeah, that's interesting when I think about it, because it does suggest that the resolution should be something like on the order of, several arc seconds. You
Well,
shouldn't be able.
again, is that the particulate in the air column?
Right, but I'm thinking. I mean, when you make a really accurate measurement, what's kind of what would you think in terms of arc seconds? What's your most accurate measurement? 1?
Oh yeah. But there again, and now you got to deal with the metrology of it. One hand clapping. Any singular reading doesn't
Right.
mean anything. But you
Exactly.
I generally take an array of about 14 or 15 repeated measurements, and then the standard deviation of that is around 1 arc second, and then that yields a standard error of about a half an arc second.
What's
And-
interesting, I mean, that's right. I mean, it sounds to me like, in some sense, you're beating Rayleigh's criterion, which you can do, right? Rayleigh's criterion, as I say, doesn't really mean that you can't see stuff below that. It's just the point at which 2-point objects will start to kind of overlap a little bit. You'll still know there are 2 objects there. So I suspect that with the surveying instrument, it sounds to me like the telescope would have a basic diffraction limit of several arc seconds. But if you make repeated measurements, and if you just, try as well as you can to line things up, it doesn't surprise me that you could get, 1 arc second accuracy out of that.
And like I said, the strobe light looks more like a cotton ball, which I don't think has anything to do with the telescope. I think it's
Right.
The particulate in the air column. And when looking at a higher elevation, because normally when looking out at terrestrial objects, you're only ever looking like about 1 degree off horizontal.
Mm-hmm.
But if I'm looking at a star at 30 degrees above, then the star is much more point source.
Yeah. No, I'm sure you're right. It's particular. It's scattering, right? Scattering makes stuff look bigger too.
And through repeated observations, like I said, even if it's a cotton ball, accuracy
You can
and precision.
estimate the center of that cotton ball.
Well,
right?
yeah, absolutely. And
Yeah.
and so you're dealing with statistics.
Yep. Yeah. No, I think that's exactly right.
Because if I go and many times in repeat observations, weeks or months or even some subsequent year, I'll still get about the same arc second at 20 some miles.
Yeah, that's right.
Controlling for the weather. Controlling for the weather meaning, what I call the weather window. None of this twilight bullshit, no night work, no winter work, but somewhere between, like 45 and 85 degrees Fahrenheit, plus or minus a half inch mercury on the barometer, and fair weather. That yields a very consistent coefficient of refraction, and I get a very consistent repeat angle no matter how many times. I can measure it, go back on 5 different measuring sessions, or I could just take any one of them. I don't even have to bother averaging because the spread is so small.
Yeah, it always strikes me. I mean, everybody should be forced to go out and do one surveying, kind of get a feel for angles, to get a get a feel for the precision and all those kinds of things. I think it's hard to really appreciate. The thing that's always hard is to kind of appreciate small angles. I mean, if you draw, for instance, light from the sun, we say it refracts downward about a half a degree. So we can see the sun, we can see the top of the sun setting approximately. No, what do I say? We see the bottom of the sun setting at about the time the top of the sun is physically setting, right? If it weren't for the refraction, it gets lifted by by pretty close to its diameter. But that half a degree, a lot of people would say, half a degree? Are you kidding? Half a degree is nothing. If you draw a line that curves along, draw a piece of paper, try to draw a line that's not straight, that actually curves downward by a half a degree, you'll never notice that it's curved by half a degree. It looks absolutely straight.
And there we come an architectural plan and profile, right? How come they don't have curvature on there? Come on, it's a few hundred feet. Yeah, you're not. You can't even with your finest rapidograph pen, you cannot draw it.
Yeah.
But
people don't have a good feel for those things.
And when it comes to, like I said, a half a degree sounds small, but half a degree is enormous. The sun is so large that I can't find the center of it.
You have that reticule, right? That's a half a degree to center things in.
Yeah, and even still, that's just too difficult to deal with. That's for rapid, I've only seen those in military surplus equipment.
Oh, so you sight on maybe the side of it or something, but never the center.
Always use the edge, because I cannot find the center to 1 second repeatability.
Yeah.
And so with the circular reticule, you could do something quite rapid. You could just, one single pop, just trying to get an azimuth for your artillery. But the whole, when looking at the edge of the sun, it looks like a sawtooth. And so a little subjectivity of how, when the crosshair is tangent to the disk of the sun. But the sun is so large. I mean, it's like, that's why you use stars, because the sun is just, where is it? It's just so big.
Well, so I'm going to suggest maybe we shut this down unless other people have questions. I probably run on and get on with my day as well, but I'm happy to answer questions, and maybe we can do this again. I do have a bunch of presentations I could give. I've given one, by the way. I think maybe in Omni's room some time ago, I gave a celestial theodolite presentation that I'd love to give again sometime.
Ooh, set that up then.
Yeah.
Do you know how to use the events?
I don't. Well, I mean, let's put it this way. I haven't done it, but I think I know. I think I can figure that out. I'll get in touch with you if I need to.
Yeah, absolutely. Because we all know celestial theodolite is pretty hot right now.
Well, it's interesting to me how many, Jesse and I take really different approaches toward attacking it. He attacks it straight on, in a very good faith way, just taking them at their word that they want to do this and doing that, and just showing that if you do that with the assumption that the Earth is, or if you, maybe I shouldn't say that. I shouldn't speak for him. I'm not entirely sure what the approach is, but at any rate, he takes the data, and just shows that it doesn't work. And it doesn't work. It never works perfectly. Sometimes it works pretty closely, but lots of times it's simply the method that they use doesn't work for obvious reasons, because the method they have says that the occlusion. It comes down to simply this: a visual occlusion of a star happens by definition at the time when the visual star is at the same place as the visual peak. That's just a tautology. That's what we mean by an occlusion. And so all you have to know about the celestial theodolite method is that it predicts a time for the occlusion that is different from that time. That's really all you need to know. And that's kind of the way I approach it, is just to show. I mean, if you want to know what the visual elevation of a peak is, just wait for a star to be visually occluded by it and ask Stellarium what the visual elevation of that star was at that time. That it's really that simple.
You know,
Well-
it's celestial theodolite.
Next video is going to
in my
be
mind, in concept, is perfect. Is great. I love it. Great, because if I point my instrument at a terrestrial object and I measure an angle of say 2 degrees, how do I know that my instrument's right? Have you calibrated your instrument? How do you know? Well, there's a star that's also at 2 degrees per stellarium. There you go. What they don't seem to understand is the refraction to the terrestrial object is about 80 arc seconds, and at that same time, at that same 2 degree angle, the refraction to the star is 1100 arc seconds. And I think that's what they just cannot wrap their head around, is astronomic refraction, terrestrial refraction, 2 different animals.
Yep. Well, did you have something to say, or somebody said something?
QOP's next video is going to be his debunk of the Cell-Theo. So when you got QOP and John on the same team, you're doing something wrong.
Oh, that's interesting. I don't know QOP well enough. That surprises me. Is that an odd position for him?
He's also the biggest TFE was fake guy. So
yeah, weird. So, but he's anti-CT.
Yeah, he's like, it's full shit. It's garbage. I don't.
Oh, that's
probably
interesting.
not. Probably for very different reasons, but they'll be fun to look at.
It would be. I mean, it's really interesting because it's really clear that, I mean, anybody who really does understand what they're doing is going to understand that it's horseshit. But it's just so few people seem to understand it. It's just really pretty simple, right? They say that the visual occlusion happens when the unrefracted star is at the same angle to the peak as the peak is to the observer. And there's also it's. I mean, first of all, that's just nonsense because it doesn't take into account refraction, and second of all, it doesn't work for all sorts of reasons. Because if that were true, then the physical angle from the observation point to the star would be the same as the angle from the peak to the star. This is a point that Jesse and I have been making for months now, and Alan and Shane just very scrupulously avoid ever addressing this very simple question. Why is it that the actual physical angle of the star from the place where the observation was made is well below the peak of the mountain?
Yep.
Yeah. Anyway, yeah, I think I'm gonna say goodbye. I will, Coco. I will set up that. I'll set up an event for doing my CT presentation. But I'll be interested if anybody gets word from QOP on when he's going to do a presentation. I'd love to see that too.
Excellent. I'll see if I can't get in touch with him then and find that out.
Okay.
All right. Thank you, John.
All right. Thanks everybody for coming. Appreciate it.
Bye.
Bye-bye.
All right, so Jesse's live stream is still running. He won't be back to turn it off for a little bit, so please just keep that in mind.